time I can tell it not to join.
It's everything is fun.
Okay, it is running. Yeah, it looks like it's live. Looks like it's recording. You guys should see it's recording.
Yep, it says,
Okay, cool. Very good.
looking at Yunko.
I know, right? Hi there. Oh, it's lovely.
Right, it can turn its head all the way around. All right.
Wow, it's like following people.
Yeah, I think that's the idea. That, right, if you speak, it should point at you.
Hello. Yes, that's working.
But we are pointing this way.
I want one.
That actually is great for use in like a hybrid classroom. That's neat. Hmm.
Now we know it exists.
Amazon. Okay, all right, well, let's see here. All right, I guess it's 10 o'clock, so we might as well start. And the meeting is being recorded. We're going to post the link up onto Slack after it's done. So if you want to go back and rewind, you can do that.
It's cutting your head off.
Yeah, fine. Don't need the head anyway. All right, so this is a little bit of an informal lecture on the basics of topology. So this is the groundwork for when you say, I have a distance matrix, or I have a similarity matrix. What's the right mathematical foundations for talking about that? So that's the idea. Topology. And think of it as space without a precise notion of distance. If you have a precise notion of distance, you can turn that into a notion of space, but it's not required. So distance is optional. And I guess kind of the best way to think about this is when you have space, you have some notion of points, places where you might be. And what topology and what a topology, noun, tells you is it tells you which collection of points are nearby each other. So it tells you a notion of neighborhoods. So let's just sort of dive right into the way the mathematics formally works. So given a set X, so this could be, think of this as points. Points where you might localize your attention. What you want to know is you want to know which subsets of X constitute some notion of neighborhood in some fashion. Which of them are reasonable to say, yes, this collection of points is somehow a neighborhood. And rather than kind of building it up quantitatively using a distance, we're actually going to build it up qualitatively. Specifies axioms. So I'm going to define topology on X is a collection of subsets. I have to name that collection. So I'm going to name that collection. Call it P for topology. And it needs to satisfy a bunch of axioms. The first axiom satisfied is, well, you could say a neighborhood that doesn't have any points in it is a reasonable neighborhood, as in there, it's the empty neighborhood. So the empty set is in this collection. So let's check the types. The types are important. So I have a set X, I have a collection T of subsets of X. So I'm using the word collection intentionally. It is a subset of the power set. So I'm specifically saying a collection is a subset of the power set of X. So collection T, it has a bunch of subsets. One of the subsets that is possible, and I'm going to ask for it to always be in this collection, is the empty set. Okay, so type-wise, the empty set has to be. The other thing, sort of the other end of that, that's like the bottom, the top is the whole. This X is a subset of X. And I'm going to require that that's there.
Can I request, before you erase anything, let me know so I can take photographs of each.
Absolutely. Good idea. Okay, so the empty set is in there, the whole set is in there. These kind of bound the size of the neighborhoods. So you can have an empty neighborhood. You could also have a neighborhood which consists of all the points that are under discussion. These are kind of the uninteresting cases in a sense, but they set bounds. And then there's two more rules that are a little more intricate. Rule number 3 says that if A and B are in my collection, then the intersection is also in the collection. It's closed under intersections. The picture here is if I have a neighborhood of points and I have another neighborhood of points and they overlap, the overlap is also considered a neighborhood. Sensible enough. What if they don't intersect? Then what is their intersection if they're disjoint? If I have two sets, yeah, it's the empty set. And hey, look, the empty set is already there. Right. So if I have two subsets, they intersect, their intersection has to be. Now, one of the things that's implied by stating it in this way is if I have 3 sets and I intersect all of them, well, I intersect the first 2, and then I intersect that intersection with the third. So I can iterate. Any finite collection of subsets, if I take their intersection, I end up with another set in this collection. All right. And then the last one has a similar character, last axiom has a similar character, but it's a little bit asymmetric. And it says if we'll write it out verbally. If I have a collection, any collection of subsets, I is in some collection, don't want to specify, take some collection of these, and I take the union of all of these. Then the union is as well. The reason for the asymmetry is I want to explicitly permit an infinite collection of open sets that I could take a union. Whereas here, I'm only requiring a finite collection. It might be the case that I could take an infinite collection and intersect them all. That's permissible, but not required. So I'm requiring finite intersections there. But intersection and finite collection, that has to be within this topology. But I'm saying, no, any possible way that you might take elements out of this set, take their union, they still are in this collection. If we do this, elements P called open sets and pair X, T is a topological space. So this information, no more and no less, defines a topological space. So whenever we want any notion of space without distance, the way you build it is you build it by building a set of points and a collection of subsets. The collection of subsets satisfying these 4 axioms gives you a topological space, no more, no less. Now, it's useful to see this in the abstract, as I've written, but it's also really useful to see this with examples. In particular, examples really elucidate why there's this distinction between intersections and unions. Because what we're trying to do is we're trying to model what happens in the case of the real line, or Euclidean space. So in Euclidean space, what is an open set? Right. But it's open set, yeah,
It doesn't include this border.
that's right, does not include the boards, that's exactly right. So what does it look like?
We draw a picture down here.
Yeah, iPhone here.
Realign with what's called the usual topology. So, an open interval, we usually write as this ordered pair, but what we mean by this, we use the colon equals to say defined. What we mean by this is the set of all points are such that, colon is such that, A is less than X is less. So notice I'm not including. So this is what an open set looks like, or at least this is an open set in the usual topology for the reals. And you might say, well, okay, if I take one open set, let's take an open set that goes from, I don't know, -1 to +1. So I can draw it with this little picture with open circles to indicate that I'm not including the endpoints. I can take -1/2 to 1/2. And consider the collection that ends up being -1/n to 1/n. You could ask, what is the intersection of all of these? What is the intersection of all of these intersections? That would be attempting to violate this axiom, because then I'm taking infinite collection and intersecting.
Just end up with 0.
You just end up with a single point, just 0. Intersection is equal to just 0. Is this a set that looks like this one? No, it's not. Why? Because if I were to say from 0 to 0, it would be X is bigger, strictly bigger than 0, and strictly less than 0. So it can't be equal to 0. So this is not an open set. So the reason for prohibiting, or at least not requiring, infinite intersections to remain open is because of this. Conversely, if I start out small and expand out, so maybe -1 plus 1/n, 1 minus 1/n, expand it out a little bit. You'll notice there's an asymptote at -1 plus 1, this expression. You'll never touch -1 and 1 if you take the union. So the union is -1, 1, and this is going up and everything. So that explains why this infinite collection is fine. Now you might ask, okay, what does this have to do with any notion of perception? You can kind of imagine that every open set that you might write down in a topology is a place where you might want to ascribe some information, ascribe some data, say that something is localized there. So topological properties that are invariant with respect to a topology are those properties that somehow respect the open sets that you've drawn. Now, the real line is one example. This is the real line. You'll notice I said with the usual topology. Are there unusual topologies you can have?
Clearly.
Clearly. In fact, this is something that is a bit of a sport among the mathematicians, is to come up with unusual topologies for things and see what follows. So let's look at some unusual topologies. Any questions before I erase this?
So one of the other topologies is usually liked. Is one that always exists. You pick any set, you automatically have two topologies for it. Two unusual topologies. The first one, mathematicians like to always try out to see, hey, does the empty set break anything? The empty set example of something. This is the trivial. So the trivial topology is the topology that absolutely smallest you could possibly make. Now, if you recall the first two axioms where I just erased them, sorry, just came in a moment ago. The trivial topology
I'm just
is
gonna post those two photographs in case you're curious, if you're in the Zoom room.
so the trivial topology. I'll just put it in equal sign. Trivial topology says the smallest number of open sets that you possibly can imagine. Just the empty set and the whole set. So for the real line, this is effectively saying if I were to put the trivial topology on the real numbers, it's no longer the real lines you're used to. It says that there's a neighborhood, which is the no neighborhood. There is no neighborhood. And everything. What does that mean? Unlike in the usual topology where some points are further away from each other, in the trivial topology, all points are basically next to each other. So the interpretation is all points are neighbors. And equally so. The other end of the spectrum is called the discrete topology. And this is the power set. So every set is open. Now, let's check the axioms for both of these. The first axiom says the empty set has to be in there. The second axiom says the whole set has to be in there. Of course, the trivial topology, that's done by construction. What about the power set? Oh, well, the power set is all possible.
Does this
Subsets.
audience know what the power set is?
I'll just write here. Possible subsets. So is the empty set a possible subset? Of course. Is the whole set? Yes, of course. So those first two axioms are satisfied. What about intersection? If I intersect the empty set and the whole set, what do I get? Nothing, the empty set. Is that in there? Yeah, of course. All right, axiom 3 is trivially satisfied with trivial topology. What about the unions? If I take the union of the empty set and the whole set, what do I get? The whole set. Oh, is that in there? Yes. Box check. So this trivial topology is a topology. What about the power set? Well, I take any pair of sets at all, intersect them. What do I get? I don't know, but another set. Is that in there? Yeah, because all possible sets are in there. Third axiom is satisfied. What about the fourth axiom? Same reason. Take any possible collection of any possible subsets. Take a union. Is it still a set? Yes. So fourth axiom is satisfied. The interpretation of the discrete topology is that all points are far apart from each other. Or not. There are no neighbors. And again, yeah, so from the standpoint of studying how points are related to each other, it's good to have these two examples in your mind to say that, well, what happens to my model if everyone's a neighbor? What happens to my model if no one is a neighbor? And of course, you can imagine then everything in between might be possible. You again have to check the axioms. So in the case of the real numbers with the usual topology, of course, it's neither of these cases, somewhere in between. And there are lots of other topologies you could put on the real numbers.
getting other topological spaces with other properties. Now, one of the things that we've been talking a lot about, and perhaps talking around, is this notion of category theory, right? Have I said anything about categories here? No, this is all sets. If you like, I'd like to imagine that there is a category of topological spaces. These topological spaces then would be the objects. What should be the morphisms? Well, they should be something that says, well, they're going to be structure preserving. They should preserve the topology that we've given in some fashion. The topology needs to be preserved. What does that mean? Well, what is the topology? It's nothing other than the open sets. So I have to preserve the open sets. Okay. So what does that mean? Well, that means that I want to be able to say how to transform the open sets from one topological space into the open sets of another. Sounds sensible enough. Let's try to do that. Okay, it's not another picture. Refresh the screen. You get it?
You want me to take a picture?
Yeah.
Hold on.
And this is this idea of asking for morphisms in the category of topological spaces.
This leads to an interesting place because this generalizes the notion of what you might imagine continuity means. And in fact, this is what this is. So I give you a definition of a continuous map,
which will ultimately be a morphism in the category topological spaces. Okay. So what we do is we say, I want to define a morphism, which I'll call F. I have one topological space on the input. I'm going to tag the topologies with the name of the set so I can keep track of it. Otherwise, things might get a little confusing. So these are two topological spaces. Okay. So what do I need? Well, I need some axioms. So this thing that I've defined is a function. So this is purely set theory. Take a point in X, yield a point in Y. Take another point in X, yield another point in Y. For every point of X, I get exactly one point of Y. But conversely, there may be some points in Y that don't have any corresponding points in X. And there may be some points in Y that have multiple X's that yield them. That's fine. It's a function. But not just any function. I'm going to give you some axioms on it, some constraints. For every open set in Y, codomain,
Which thing is the codomain, X or Y? And you're doing
Y. Note that. Good question. Oops. No, put that. Codomain. So for every open set in the codomain, I'm going to ask for the following set, which I'm about to construct in the domain, to be open. We write it like this. Define it for you. It's the set of all x's such that when you apply f to that point, it lands somewhere in this. This is called free image. So mathematicians like to say every open set has an open free image. And you'll notice there's some ambiguity that is apparent in stating it this way. Because I have two possible notions of open sets, but it's actually unambiguous once you realize the pre-image has to appear in the domain. So then this open set here corresponds to the codomain. This corresponds to the
Can you notate that on your?
I will notate that. So this is. This domain. So let's take a picture. Okay, now you might ask, I want to philosophize on this for a moment. You might ask, why are we going backwards? Like, wouldn't it be more natural to say every open set in the domain gets mapped to an open set in the codomain? That would feel more natural. And it turns out that if you try that, you get a well-defined thing. However, there's a bit of a problem. And the problem is that forming images of sets, because I can collapse two points to the same point, functions ascribe exactly one y to each x. But not conversely, that's an asymmetric condition. Due to that asymmetry, if I take unions in the domain and then push them forward, or if I take intersections in the domain and I push them forward, I don't get unions and intersections here. There's subset. However, if I build pre-images of unions and pre-images of intersections, again, because of the asymmetry of that function, pre-images unions and intersections remain unions of and intersections of sets. So it preserves this structure that is exactly what we want to talk about when we want to talk about a topology. Remember, the axioms 3 and 4 of the topology said I have to be able to take unions of any kind and intersections of pairs. If taking pre-images preserves that, that's good. If taking images, going the other way, does not preserve that, then that means if I have two sets that I take their intersection of over here, it might not be the intersection of two sets over here. And that's a problem. So by looking at pre-images, we preserve that intersection and union structure. So that's why it's defined this way. It's a little counterintuitive, but this way actually preserves all of the topology structure. I take two open sets, I can intersect them here in the codomain, take their pre-image that's still open, or I could take those same two sets, form their pre-images, and take the intersection here. And it's still exactly the same set and is still open. Doesn't work the other way.
Was it kind of like a branch cut almost?
It's kind of like kind of this the idea. And in fact, branch cuts are an expression of a discontinuity.
Then like there could be an open set that has a non-open pre-image, but we're just not going to use those ones.
Absolutely, that's exactly right. We're only looking at the open sets, and we're asking only those open sets to have open pre-images. There may certainly be non-open sets who have open pre-images. They're not under consideration in this definition.
I'm at the other way around.
If I have a non-open set here and it has any kind of pre-image, I'm just not even looking at it. I'm only looking at open sets.
No, like an open set
Mhm.
in the codomain
Mhm.
is not necessarily open in the domain.
I'm asking for open sets in the codomain to have open pre-images.
Are you saying that you can only use those ones, or those are the only ones that exist?
Those are the only ones under consideration for this definition.
Okay.
Yeah. Other questions? This is kind of something. And when you look at this, you say, wait a moment.
That's a
Maybe you do-
question.
Based on the choice of the function f,
Mhm.
can you say something about the topological space Ty? Or does it constrain-
Absolutely. Absolutely. This is actually the business of using category theory to study topology. The business of, because ultimately these open sets are going to be morphisms in our category of topological spaces. What this means is we could take a set theoretic view, which is what I'm taking right now. Build things up by sets and asking what happens to those functions. Or I could say, you know what? I'm just going to take a structural perspective. Look at the structure of these continuous maps without ever actually introspecting on their points. Looking at how they relate to one another. For instance, talk about categories. There's a notion of isomorphism in a category. Yeah, right. Isomorphism tells me when two objects are equivalent somehow. What does that look like here? Well, an isomorphism has to be a morphism with a sensible notion of an inverse morphism. What does that mean? Well, if I were to do that here, I flip the role of domain and codomain. So I'm saying if F is an isomorphism, there's another continuous map that takes me from the codomain back into the domain. Such that, well, first of all, it better invert the function itself. So it better be one-to-one. It better be onto. So it inverts the function. And guess what? It's all of the open sets of the domain of the original function do in fact become open sets of the domain. What does that do? That sets up actually a one-to-one correspondence between all the open sets of both sides. In which case you're saying, these topologies are actually exactly the same. This is actually too strong. This notion of isomorphism in the category of topological spaces has been a thorn in the side of topologists since they came up with the idea. And most of the time, and in fact, historically, part of the motivating reason for category theory was to relax that condition. Now, I've said a lot that I haven't written. Should check that out. First of all, what I was going to say before that momentary digression was saying the word continuous map. Does this look anything like, if any of you have taken calculus, does this look anything like continuity for calculus? Do you remember the definition of continuity for calculus?
Got a limit in
It's
it.
got a limit in there, right? There's like, or
Not
intuitively,
seeing
like you could draw the functions graph without picking up your marker. Yeah, remember that? Maybe, maybe not. Does this look like that? No,
Not really.
not really. So let me give you some examples. I'm going to give you an example of a function which is continuous and a function which is not continuous, side by side. You'll be able to visually see, yeah, one of them, the marker had to get picked up, and the other didn't. But you'll be able to see that in the case where the marker got picked up, we violate this axiom. Whereas in the case where the marker stayed down the whole time, this is set. Right, so erase this. That's so I'm going to draw two graphs. Of two functions. Both of them, I'm going to put the usual topology on the reals on both the domain and the codomain. The domain is the X, the codomain is the Y. And here is F. Now, if you're in a calculus class, this would be a quite sufficient diagram.
Is that a Y over there?
Y is equal to G of X. This very nice
Does
one.
not look like a Y.
Very
There you go.
better. Okay. So,
So like, are there open circles close?
okay, very good question. Question. Thank you. Must be a plant.
I really wanted to know.
Right, if you're in a calculus class, this is sufficient. They say, hey, look, I picked up my marker,
That's discontinuous, full stop. And if I take a limit from the left and a limit from the right, they're different, so yeah, not continuous. That's not sufficient for our level of precision here.
we need to actually know what value to ascribe to every input value of this function. What value of y goes to what value of x? And here, okay,
Actually, I'm happy for audience participation. So what value would you like?
Well, I'm skipping, but commutative diagrams will solve this.
What commutative diagrams would solve this? Yeah, that's like using a sledgehammer to kill a fly.
Okay.
Could they use like x plus and x minus and the two values?
I have to pick one value. It's a function.
Three, just three.
Three. Put it three. I'll call this three. Very good.
okay, and so if it takes value 3 at this x value, which I don't even care what the x value is, if it takes the value of 3 here, it
Cannot take a value over here.
because every input has to have exactly one output. If I'm committing to this output, I can't have that.
Fine, draw it.
All right, so now let's run the definition of continuity. Let's see how this function is continuous. And this is
Mostly continuous most of the time,
except there's this big jump. So
what do I have to do? Well,
I have to take every open set in the codomain, the y-axis, and look at its preimage.
so let me pick an open set. Pick an open set that looks like this. So it's a little open interval in Y.
I've made a little horizontal segment. I'm not including the endpoints. Now my job is I have to tell you all of the x values that will land you somewhere in here. Okay, well,
What about this X value? Where does this X value come from? Or Y value? What?
Where's the three on that axis?
Well, that's.
there's
I say. Okay, so we take this point and pre-image. Which values of this function, or which X values for this function will get us to 3? I guess if I look at the graph, this one. Right here, this value.
If I take this x value, no, looking at the graph, I know, we're right there, and that's
Inside.
all right.
Do it for 3.5. Do it for 3.001, whatever.
Fill them out.
I can fill out every such value up to, but not including this upper value. So that means all of these values down here are in the preimage. What about on the other side of things? Well, all of these values are in the preimage. So the preimage of this open set looks like this open set.
Can you label that pre-image?
I'll call this one U sub 1, and I'll call this one F preimage U sub 1. This is the preimage.
Thank you.
This was an open interval. Is this an open interval? Yeah, doesn't include the endpoints. All right. What about a different one?
If I go down here.
Well,
I guess the smallest value of X that will get me somewhere in this interval is over here. What about the largest value of X? Well, all of these values of X kind of get me into this interval. The largest value happens to be on the other side. That's okay. So this is U2. This is preimage of U2.
is it still an open set? Yeah. And you can kind of see everywhere that I try to put an open set, its preimage will remain open. Why? Because I won't touch the endpoints somehow. Let's see what happens over here.
This whole continuous curve piece, so to speak, over here shouldn't present any problems. If I forgot everything
to the left of this jump, it's basically the same situation. But what if I take this same sector, this U1 set, including 3? Which values of X will get me into this subset? Well, as before, the upper limit's no problem. Everyone down in here along this segment of the curve will land me into this little region on Y. So if I start with an X value over here, I end up with a Y value up here. So all of this is definitely in the pre-image. Right? And in fact, that remains true down all the way up to this last point. All of these points here, if I pick the X value over here, my Y value will still be within this specified U1 interval. But what about this last point, the point where the jump discontinuity actually occurs? What value do I take at this X value?
Color it in.
Color it in 3, right? Because I land at 3, 3 is within my interval. So that's definitely there. But what about if I go further to the left? If I go right here, where do I end up? Down below. Is that in my interval? No. So the pre-image of U1 is well defined. It exists. But is this an open set? No, this is not an open set.
So why do we care? Why do you not want to let that be part of the?
Okay, because this means thus G is not continuous. We've detected a discontinuity by a change from an open set to a non-open pre-image. Whereas over here, every open set has an open pre-image. It is continuous. So this is the distinction between continuity and non-continuity. I realize this is not a proof. On the other hand, a proof is probably not very enlightening. There is a correspondence, in fact, that you could write down and say, all right, great. Everything that you learned from calculus, or perhaps did not learn from calculus, still remains true. But this is a massive generalization. Calculus involves things like the real number, right? Derivatives and integrals. It does not really work very well in the finite world. Right? Calculus involves taking limits. Where are the limits in this picture? I never asked for the word limit, did I? So as such, I don't really need them. This is actually a real benefit. And so what I want to now do is do a little bit of so kind of see this machinery generalizes some of the classical mathematics, but yet it can do some things the classical mathematics can't do. So if you remember on Wednesday, my starting point for the sheaf discussion was, I'm going to start with a partial order or a pre-order, depending on my particular mood. I'll explain what that is in a moment. But I said, start with a partial order or a pre-order, and then I'm going to build my sheaf on top of that somehow. And I made some sort of side remarks that we're actually building a topological space that way. I want to show that to you now, because I think this is actually very valuable. And it's a reason why this generality, the general machinery, is, I think, something you want to have in your toolbox. Saw you snap pictures.
Oh, very 30,000 feet view. So all of this, I mean, if we look at that, we understand there's a discontinuity.
Absolutely.
There, but it was basically showing something concretely here that you can use. It's a more general apparatus.
Absolutely.
And so that's because when we're interested in topology, we're interested in spaces. So continuity is very important as
such.
Discontinuity.
Absolutely. Right. So if it detected, so the failure of continuity says, I mean, from a category standpoint, this is not a morphism. Whereas this one, when I'm in the process of erasing, this is a morphism. This is a morphism. Actually, it's an endomorphism. Morphism from a topological space back to itself. This is an endomorphism. This is not. I mean, if you want to use that sort of category theoretic high level language.
But it's sort of at the ground state. This is telling us this apparatus is a strict generalization of the classical mathematics that has been used for many years.
And so if we wouldn't have chosen 3 right there, if we would have left it open, then actually we could have made this continuous.
Ah, but where do you put that value? You have to put that value somewhere.
And then kind of thing.
Well, no, okay, look, Siri, tell me what value this X value needs to take in Y.
I can't make that. I can't budget, I guess.
Right, you have to commit to something because it's a function. Any value you commit to will yield one of these problems. So if you were to say, well, let me make it down here, well, then I have this problem on the other side. You say, well, let me put it in here. Oh, well, then I could just like take a teeny little interval like that, and now you pick up a single point, not open. Oh, put it, same problem. Anywhere you put the value of Y value of this function on for this X value is going to yield a contradiction to the axiom of continuity. So this is not a morphism. No way, no how, cannot be fixed. The only way you can fix it is by saying, oh, actually, I don't like the topology. I'm going to swap the topology out for something else. Change the topology, and then you've changed the rules. And then you have to recheck. Your intuition about those topological spaces will be different. This is, in fact, the subject of like much of a traditional point set topology class. Is then we say, all right, let's change the rules. Let's see what breaks. Let's change the rules, see if we can get some intuition for it. It's all very weird.
The topology here would be R square or Euclidean.
This is just Euclidean space on the real line. Euclidean space on the real line. Input, output.
Yeah.
Yeah.
The only way to do that is to remove that point in time.
Yes, that's like a surgical change.
And then you get a completely different.
And then you have a different topology. Exactly.
But you have to accept it, either that or.
That's right. This is an immovable obstacle. And if you want it gone, you need to change something substantially. Yeah.
Is topology in a way a bridge between calculus and geometry? Or let's say.
Kind of. Topology is a bridge between actually it's sort of like the on-ramp to calculus in a sense.
Yeah.
If you're doing calculus, it implies topology. If you're doing calculus, it actually implies specific kinds of topology like this. Do you need to be doing calculus from a modeling standpoint? Ask yourself that question. Do you need the apparatus of calculus? If you don't, and I submit that actually you tend not to, then just using topology is sufficient. And that's what I want to show you now. So I mentioned, as I said, this notion of starting with a pre-order or a partial. And this is really good for studying hierarchies. Anything where there's a hierarchical structure looks this way. So topically, this is the Alexandrov topology. Alexandrov topology is for hierarchies. And the way that we start is a little bit different. Same set X. Start with the same set X. But now, with a relation, which I'm going to write as less than or equal. This is meant to evoke less than or equal to from the real numbers. I'm going to satisfy two X's. If I have an element of X, X is less than or equal to itself. Well, like if X is the real numbers, 3 is less than or equal to 3. Sounds sensible enough. Of course, it's equal to 3, right? But it's definitely less than 3. The second axiom says, if X, Y, and Z are X, and X is less than Y, and Y is less than Z, then X is less than Z. Seems sensible enough in the real numbers.
1 is less than 2, 2 is less than 3, so 1 is less than 2. Less than 3.
Still hung up on one, why is it?
'Cause
Equal or small, like, why is it just equal? Why is it just identical?
Oh, okay, all right. In fact, here's the answer to your question, but perhaps sideways. If x, y, x, and x is less than or equal to y, and y is less than or equal to x, then x is equal to y. This allows the difference between these two axioms allows me to talk about things which are at different levels. So the case that you're imagining where you've got 1 is equal to itself or 3 is equal to itself, well, 3 is yes, then in fact it's really. Of course, that's kind of a trivial case. Now, satisfy the first two axioms, we get what's called a pre-order. Satisfy these 3 axioms, you get what's called a partial. And the thing to realize here, I'll draw a picture. Two pictures kind of fixed in your mind. I'm going to use arrows to indicate the less than or equal to. So by this, I mean A is less than or equal to B. This is a partial. I'm not going to draw in the self relations that are implied by axiom 1, but what you can see is B is less than A. Right? And so by the second axiom, this also is true. Because D is less than B, B is less than A, B is less than A. Similarly, there's one more arrow that I have not drawn. Here. Right. So this is a satisfies the first axiom by assertion, just because I didn't draw them. Satisfies the second one because I'm adding these 2 extra arrows. These are implied by axiom 2. And the last one, if I have B is less than or equal to, let's try it. Is B less than or equal to A? Yes. But is A less than or equal to B? No. So they're different. Is B less than or equal to C? No, not really comparable in any way, and not so the other way either. And you could walk around the diagram and check that this axiom is satisfied as well. Now let me draw you a partial pre-order, which is not a partial order, and I'll be a little bit more simplistic than that. Start with the same kind of diamond structure that was present before. Yes, you're right. There's a category theoretic connection here. Sure.
Is that word AD, is it an and?
Here.
Nope.
Yes. This is now a pre-order, which is not a partial order. B and C, B is less than or equal to C. C is less than or equal to B. And yet they are not the same. So this is a pre-order, but not a partial. Whenever you're dealing with hierarchical data or hierarchical models, you can think more or less specific. As I usually structure things so that the more specific things are higher in the relation, the less specific things are lower in the relation. So, kind of to give you an idea here, an interpretation, here are vehicles. Here's a boat. Here's a car. There's a Honda Civic. And here's one of the other cars we have,
Mazda
Mazda
5.
5. And in fact, we could even be a little more specific.
Where's
Say,
the boat?
my Honda Civic. Anytime you draw a Venn diagram, you're really drawing one of these. by drawing the nesting structure. Now, having laid down,
Wait, are you saying there's two civics?
this is Honda Civic in general as a topic.
Oh.
A specific topic is my Honda Civic. A less specific topic is just a car. My Honda Civic is definitely not a boat. If it were, I will need a new Honda Civic. On the other hand, both a Mazda 5 and my Honda Civic are different kinds of cars. So this is a way to formalize Venn diagrams.
Can you give an example of the B and C where they're less but not a partial order?
Yeah, so pre-orders crop up in interesting places. So you could say, yeah, I have two, I have actually, instead of talking about specificity like this, there are two things which are not very distinguishable. So hold on, let me
The
think
chicken and an egg.
Oh, two Mazda 5.
Right, two Mazda 5s, sure. I've got a Mazda 5 here, another Mazda 5. They're not the same Mazda 5, but they're both cars. And in fact, they might even be owned by us. That would be a nice situation. Unfortunately, they don't make it.
But then what does it mean to have the arrow? between them?
And the arrow is again some kind of it's some kind of specificity relation, saying that we're getting more specific as you follow the arrow. So a Mazda 5, okay, that Mazda 5 right there. More specifically, it's a Mazda 5, just like that one. They're somehow indistinguishable. It's a little.
They're kind of at
But
this,
then how can I go from there again?
but that's
Get
why
more
it's,
specific.
It's
comes
in
to-
fact,
but
in
that's
fact,
why
I have
it's less
changed the
than,
level.
but that's why it's less than equal, because it's staying on the same
Right.
level.
Right,
It's
or
allowed to
equal.
have any.
Right. So it's not actually getting any more specific, although I'm trying to get more specific in a sense.
The same way like monotonic doesn't have to be increasing.
Yeah, it's that, and there's a good reason for that, as we'll see. Looking at the time, we've got about 5 minutes, and I can turn this into a topological space. Put a topology on this, and then you will see how this works. Yeah, Mika, do you have a comment?
Yeah, so Alexander topology is like a specific kind of a partial order.
An Alexandrov topology is yet to be defined by me, but will be momentarily.
Ah.
Okay, so we have sets with this relation. A relation is not a collection of open sets, is it? And so therefore it cannot be a topology because of the wrong type. Let's fix that problem. Let's tell you which collection of elements are open sets according to this. And in fact, the idea is very simple. So I'm going to compress. I'm going to compress starting data. Start with the pre, which could be a partial order, but it's a pre-order. It's the smallest topology, which I'll explain what that means in a moment. So it picks up all of the sets that are upwardly closed. So again, picture helps here. I'll recover my vehicle diagram here. And what I'll do is I will draw these sets. These sets here are the upwardly closed sets, or sometimes they're called the stars. Used that term last week. So the star associated to my Honda is just the elements of this partial order that are above my Honda or equal to my Honda. How many of those are there? Oh, just that one. So this is U subset my Honda. What about this one? Well, just go upstream from that. So you pick up just these two here. What's another open set? Car, Honda, my Honda, and a Mazda. Of course, just both on its own. There's one as well. Now,
Can I have a vehicle in the rest of it?
aren't you good? I don't want to run out of space, but yes, absolutely. Vehicle plus everyone as well. And all right, now comments. Is this set closed under intersection? Yes, right. If I take the blue set containing all cars and I intersect it with my Honda, what do I get? Just my Honda. If I take all cars and I intersect it with all boats, what do I get? Nothing. Empty set. Empty set. Sure, fine. Okay. What about if I take the union of both with Honda? That's not one of these sets. This is why I've asked for the smallest topology containing at least the following. What this means is you add in all the unions as well. And then that forms a topology. That statement, this is a theorem, says that if you add in just the unions to this collection, then in fact you get it. This is the Alexandrov topology. And this is really, whenever you're talking about a hierarchy, a partial order, or a pre-order, like we did when we're building our sheaves, this is the topology that's applied. It's 11 o'clock, so officially we're finished. I'll have to take questions.
Asking you said, before we went to the Alexandrov topology, you said the relations don't give us open sets.
That's right. Because a relation, what is a relation? It is a subset of all possible pairs. A relation says which item pairs with which other item, which item pairs with which other item. It's not a subset of the wrong type. So if we want to ascribe the right types to things, to say, oh yes, this, if I'm talking about open sets, the open sets are subsets of the original set. A relation is a subset of ordered pairs. Wrong type. This gives us clear subsets. And moreover, I can say this separately as a theorem, which requires proof, but it's not hard. It is that this operation turns partial order into a topology. Is there a category of topological spaces and continuous maps? Yes, that's what I'd said. Is there a category associated to partial orders? Yes, there is. In fact, there is a category of partial orders. Of course, I haven't defined that for you, but there is such a thing. And this process of building the Alexandrov topology, as shown, is actually functorial.
No, but you said this starts with a pre-order.
Oh yeah, partial order is a kind of pre-order.
So does this work with pre-orders also, or is it just with partial?
This works with pre-orders, and therefore it also works with partial orders. Partial orders are a special kind of pre-order. This works on the more general object.
So is the Alexander topology more like a tool to extract certain properties from partial ordered sets.
Exactly, that's
So
exactly what it
it's
is.
not exactly a Alexander topology like its own that is different from partial ordered sets,
Yes.
but it's like a tool.
Right, and actually, there's a famous theorem of Birkhoff that says that every topological property that you can ascribe to the Alexandrov topology has a reflection purely in terms of the preorder. Everything that you can learn about the preorder, you learn from the Alexandrov topology. So not only is there a functor that goes between the two, not only is that there a functor, that functor has an adjoint, and moreover, that adjoint is actually an isomorphism.
The functor is between.
The category of partial orders and the category of topological spaces. If you're dealing with finite partial orders and finite topological spaces, everything inside is finite. The theorem of Birkhoff says those two categories, where I've restricted my attention just finite, those two categories are equivalent.
The category of categories.
No, category of finite partial orders and the category of finite topological spaces. Those are equivalent. Finite is absolutely essential. You say not finite, everything goes to hell. Yes, absolutely. There's actually, as a result of this and implications of this, there's a really nice book by Barmak on algebraic topology of finite spaces. It basically says, okay, everything you want to do with a topological space, you can reflect it back into partial orders, study it there. So all of the machinery that then I've shown you the door. If you go through the door and study topology, there's lots of things you might study. You say, oh, are they true here? The answer is yes, many of these constructions pull back very nicely.
I actually even struggle with the notion of a finite space.
Here's a finite space.
To be discrete, that it's.
No, just, okay, this is a finite space right here. How many points are there? 1, 2, 3, 4, 5, 6. Full stop. This is a space with 6 points.
It's
That's-
also discrete though.
Okay, but let's be very precise about language. Discrete means that every possible set is an open set. It has the discrete topology. This, I'm prohibiting certain open sets. I do not have an open set that is purely Honda, but not my Honda. So this is a finite but non-discrete topological space. And my experience has been, as I said on Wednesday and shown by examples by Donna as well, finite topological spaces are really good tools for modeling.
But what makes it a space? I mean, it almost sounds more like a set.
It's a space because it is a topological space. It is a set with a topology. It's a set with a topology. Which topology? This one that I have built for you.
The topology is the preorder.
The topology is generated by the preorder. The preorder tells you it's a recipe for building the topology.
But what makes it a space? That there are relations, there's some kind of structure to it. or-
That space is the topology, nothing more and nothing less.
But topology is what? Is the structure or the ordering?
Well, he's put this rule, you can't talk about Hondas unless you're allowing us to also talk about my Honda, for example.
Michael, maybe you should remind about the notion of what open set and the notion of how open set relates to neighborhood and neighborhood relates to
Uh-huh.
space.
Yes, that's exactly right. That's a good point. So if I'm sitting on Honda and I want to know what is the neighborhood of Honda, it's an open set that contains Honda. There are many neighborhoods of Honda. There's a very fine neighborhood. The very smallest neighborhood of Honda also includes my Honda. There's a larger neighborhood of Honda. Be less specific, just cars. That's also a neighborhood of Honda. Oh, actually, another larger neighborhood is all vehicles.
It's actually kind of like cascading style sheets.
Yes, you're right.
Totally getting, so there's a spatial notion when you say neighborhoods.
There's a spatial notion of neighborhood. It's sort of a semantic neighborhood here rather than a spatial neighborhood. Mathematicians say, all right, fine. Anything that is a topological space, we just abbreviate. We elide the topological adjective. We say just space. We mean topological space. Or at least when you're speaking to a topologist, this is context dependent. Yeah.
So, do I understand correctly that the main operating tool for category theory is the partial ordered sets? Generally.
It is one of many. If you want to code up anything in category theory on the computer, you're going to be talking about something finite.
I'm thinking that this seems to be, let's say, after a while of digestion, this is kind of simple.
It is kind of simple, but it's, you know, this is the whole point of math, right? You get the absolutely as simple as possible, but no simpler. That's kind of what we're talking about here. We stripped away all the complexity. And we're just left with what's left. So
Can you explain one more time why this is non-discrete?
okay, what I'm
But by this definition.
by this definition, that's right. I'm using the word discrete in a very specific way. I mean the discrete topology. The discrete topology is the topology which contains all possible subsets or neighborhoods. So in the discrete topology for this, which I could write down, the discrete topology for this says, oh, well, actually, Honda alone is a neighborhood. Then you can consider Hondas without considering mine.
I guess,
You've destroyed that relationship.
what would be a non-discrete topology?
This one. This one is non-discrete. Because
I
every
thought you
time
said
you
this
talk
was
about Honda,
discrete.
no, if you were to talk about
No, sorry. Is there a continuous one?
continuous function. Okay, continuity is an adjective applies to functions. So you would need to transform this hierarchy into something else. Make a function from this partial order to some other partial order. For instance, you could say, great, I'm gonna take this partial order and I'm gonna map it to dollar value. Dollars is another partial order. Actually, it's a total order. How expensive is it? Well, in fact, you'll find that that's not continuous. Why? Because if you go from what's the
Is it gonna
price
be- is
for
it gonna be-
a Honda?
It'd be a range, right?
That's right, it's a range. It's not really sensible to talk about that sort of thing.
But maybe you could say,
All right, I'm going to talk about a
No, this wouldn't work because my Honda has a book value of 0 and that would be a limit.
Fair enough. Fair enough. Robert,
Is this a T2 space? Is this a?
okay, no, this is not Hausdorff.
No,
Okay. It's T0. So actually, key theorem, all right, for those who know the distinction, every pre-order yields a topology. Every partial order yields a T0 space.
It is a Kolmogorov, right?
Yeah, it yields a T0 space, which is to say that you could separate on one side. And effectively what that says here, which you can see very, very clearly, is let's take a set, Hondas. Let's take a point outside the set. Car. Is there an open set that contains, or that contain, or well, I'm sorry, said that wrong. Let's take car and Honda. Is there an open set that contains one but not the other? Yes, that red set here contains Honda but not car. So T0 says if I have 2 points that are not the same, is there an open set that contains one but not the other? And that happens here. That does not happen if you have a true pre-order. That's not a partial order. That fails. Now, Hausdorff says, in fact, are there 2 open sets that are disjoint that contain one and not the other and one and not the other? That doesn't happen here. This is not a Hausdorff space.
Because I was a bit confused whether the boat and car would be disjoint.
Yes, that's right. There's no reason why you have to have it that way.
Yeah.
But what's guaranteed, if you start with a partial order, build this Alexandrov topology construction, you'll get a T0 space.
It's almost 1/4 past.
Any other questions? All right. Nope.
I have a silly question. So given that the requirement for this topology is a partial order,
a pre-order, yes.
right?
Well, okay, so this works with a pre-order.
Yeah,
Mhm.
right. Okay, so then my question does not apply.
Okay.
So the question was that every partial order can arguably be extended to a complete order. So we do the property that you can deal in that order.
Yeah, if you turn my partial order into a total order by squashing it somehow, like I was trying to squash this into price.
Yeah.
Then you very likely end up with something that's not a continuous map. I.e. not order preserving. Squashing a lot, exactly.
Let me think about it. I
Yeah.
was thinking about, Peerlite, extension theorem. Or I don't know how to pronounce the name, sorry. But yeah, well, I can ask you later with the reference.
Fair enough. Yes. Okay. All right. Well then. That's that.